I'm Richard Milton, and this is the Small Changes Quant AI Resilience project, which if you say it right, it sounds like SCQUAIR. I'm not sure that was a great name for a project, but what it does is it takes an existing model, which is the QUANT model, which is Professor Michael Batty's spatial interaction model. Now, QUANT is a travel to work model, so it's modeling people going from home to work and back again every day on the transport networks. Now, QUANT is based on census data. So it's based on the question, where do you live, where do you work, what mode of transport do you use? So these are the four modes of transport that we've got. We've got an active transport network, the cycle network, we've got the road, the bus and the rail. And what these show are flow maps of people going from home to work. Each of the little arrows, I mean, you can't make out the arrows at this scale, but it's the UK scale. The arrows are a zone in the model. So this is a big model. This has got 8,436 zones to the model. So each origin zone has an arrow which is showing an average direction of flow. And also the length of the arrow is proportional to the number of people on the flow. So if you look at the bus and the rail, you can see that it picks out quite effectively, all of the job centres like, the Leeds, the Manchesters, the Liverpools, the Glasgows, and specifically the London. So that's flows of people, but the people have got to move on something. So we have these transport networks. I haven't shown the active transport network because it's much too dense. It's basically the road plus a bit. The road network has 8.5 million nodes to it. The road network is built from the OS roads network with the speed limits, so we know how fast they can go on the roads. The bus and the ferry network is a different kind of network. Although it actually uses the road to transport the buses around, it's built on a timetabled network, and that has about 500,000 edges to it. Now, the rail network is slightly different. I've shown two rail network diagrams here. The red diagram on the left shows the actual physical rail network. This is the actual track that's down there on the ground. The map on the right is the timetabled network. So that's what we actually use for the costs in the model. So these networks form the costs for the spatial interaction model. So population centres that are bigger and with more jobs attract more people. Things that are closer attract more people. It's essentially a gravity model. So that's flows of people and how the QUANT model actually works in a nutshell. This is the project. So work package 1, we implement QUANT on DAFNI. Now, the idea for doing that is that we can then run large numbers of batches of scenarios. So to date, we run about 12,000 scenarios. We'd like to ramp that up by a factor of 10 or 100 by using the DAFNI platform. Now, once we've generated all those scenarios, we can then use those scenarios as the training data for an artificial neural network model, which we can then teach to build its own scenarios. So the idea is that we could use either an existing scenario that an urban planner has built and say, okay, optimize this for the carbon budget, improve this model, or we can use the ANN to build its own models from scratch. Work package 4 is to visualize, analyze, and write papers. But the outputs are a portfolio of plans and scenarios for the UK, but also we're committed to doing some workshops, which I'll come back to in a minute. Now, I need to show what a scenario is at this point. So I'm going to use the Heathrow third runway scenario. Now, the green outlines show where the government white paper is predicting that there will be either primary or secondary jobs as a result of a new airport right where that airport symbol is in the yellow in the middle. So that's the Heathrow zone. Now, if you look at the map behind it, the choropleth that's on the back, the coloured map, that's showing where the QUANT model is predicting that people are going to want to live or even have to live due to the transport infrastructure in order to get to those jobs. Now, what I've done is I've shown only the road mode of transport. So effectively, that's your carbon budget. That's where people are going to want to drive to these new Heathrow jobs. Now, if you look in the bottom right corner, where it says road 727,000 kilometres, that's 727,000 kilometres added to the road network every day by people driving to these new 65,000 jobs. So that's a lot of extra kilometres driven. That's a really bad carbon scenario. And it's largely because it's right slap bang on the green belt. It's actually splitting the green belt. So let's see if we can improve on that. Let's put a rail line in. So what we've done, I've put a rail line from where a lot of people are driving in one of those clusters. I've jumped where the green belt is, where I haven't shown the green belt on the map because I've run out of colours. Basically, there's too many things on that map as it is, and maps are supposed to be what I do. So the blue line is a rail line. Okay, I put a simple one in just to show you. You look at the number at the bottom bottom right. 725,000. I've knocked almost 2,000 kilometres off straight away. Okay, let's do a more complicated one. Now, this is quite a complicated set of changes. So you can see why I want the computer scenarios. You know, when you're an urban modeler and you're staring at this and you're looking and you're thinking, where do I put my rail network? It's based on a whole load of really complicated data about networks and about population and employment that you've got to take in and understand. But look at the bottom figure, 529,000 kilometres. Just by doing that, I've knocked 200,000 kilometres off of the road network. That's worth having. But in terms of human urban planners, we run urban planning workshops where we've got professional urban planners to come in. And it turns out the first thing that an urban planner does when you say you can build anything you like, they go and build on the green belt because they're not allowed to do it most of the time. So this is the SCQUAIR plan here, the square with a cross in it. This is possibly where I got the project acronym from. But the SCQUAIR is sort of like a classic star network. What it's doing is it's bringing people from outside sort of the extent of the green belt, bringing them into the centre of London via that cross. Now, I built the circular one. Now, for some reason, it turns out that this was a fluke, I have to say. I'm not a professional urban planner. My one generated 10 times the impact that the SCQUAIR did. And it's interesting because it's getting towards what we call the small changes scenario. So the idea behind some of this was to use the computer to do the analysis of the data. There's a theory that says if you take a project like HS2 and you break it up into lots of pieces, so it's a big, complicated, expensive project, break it into lots of smaller pieces, lots of smaller projects, you effectively de-risk your projects because you've got lots of smaller ones. And the potential is you can actually generate more overall impact from this by building projects geographically all over the UK instead of concentrating them all in one area. So here we've done 300 random bus routes. These are just random bus routes to see how much impact we can generate. The white lines are the random routes, and they're just basically ribbon networks. I've picked out two of them in red, just so you can see what they look like individually. But you've got one goes under the centre and one goes to the left of the centre. So those are network scenarios that we can analyse. The other one is basically just job swaps. So the idea is you swap the numbers of jobs so that you swap people around to reduce the amount of distance that they're travelling and try and improve your carbon budget. But you can also do it for levelling up scenarios. So I had to show we've compared this to real world scenarios. So the coloured clusters, the orange, the grey, the yellow and the blue, the clusters are actually the computer scenarios in sort of groups of 300 or 600. The stars are real world scenarios. So you see the green star in the top left, massive HS2 project. But you see how they sit on a 45-degree line. Basically, as you move from the right to the left of the diagram, you're reducing carbon. So that's reducing the number of kilometres being driven on the road. And as you move up the diagram, the projects are getting physically bigger. So you're sort of sitting on that 45-degree line, but you can play around with it a little bit. You see, the one that really jumps out is the Camcox, which seems to punch above its weight for impact. So these are all cost-benefit charts, which we have to use to compare to real-world scenarios. So to finish up, we haven't looked much at network resilience yet as a metric. We've looked at carbon, we've looked at a few other things. I wanted to show the three networks here, just to show how physically different they are. So the road, the rail, and the bus, They are the same geographical location. They are actually London. But you see the difference in the look of the three networks. The rail is really sparse, the road is really dense, and the bus has some issues with connectivity. And I'm going to leave it like that and just say that it's basically all about job accessibility. It's about getting the people from where they live to where they work on the existing rail networks and then home again afterwards. Okay?